So in this problem, we're asked to determine the deflection at point A here. All right, and we're asked to specifically, we're going to ignore the shear component. All right, so in order to do this, we can use Castigliano's method. So we can say that delta A would be equal to the derivative of U with respect to the force applied at point A. Okay, so in this case, our force applied at point A is P. All right. Now we know that because for cases where we have transverse loading like this and just bending, we can actually use the simplified Castigliano's method, which says that this integral, or this derivative here, is equal to the integral from 0 to L 1 over e to the I z mz of x times the derivative of mz of x dp time, and we're going to integrate over along the beam from 0 to L. Okay, so that's our main equation. Okay, so in this equation, we have E and I are typically constants, but in this case we have a stepped shaft where the moment of inertia is twice as large in the second part as in the first part. So what we're going to do is we're going to actually break this equation into two parts. We're going to say that delta A is going to be equal to the integral from 0 to L over 2, 1 over E I1, alright, times mz of x dmz of x dp dx. Okay, and then our second plus a second integral from L over 2 to L of 1 over e to the I2 mz of x dmz of x with respect to our applied load P dx. Okay. So that we know or could calculate all these terms here. So the only thing that we don't know is we don't know what mz of x is right now. Okay, and we don't know what dmz of x with respect to P is. All right, so those are our unknowns. So we're going to solve for those, and once we solve those, we can then solve for delta A. Okay, so let's figure out. So what we're going to do to find out what mz of x is, we're going to take a section cut at some arbitrary location x along our beam. So if we take our section cut here, we know we have our applied load P. It's at a distance x from our section cut, and at our section cut we'll have our internal force, our shear force, and our moment. Alright, but our moment is really the only thing we care about here. So if we sum our moments about x and we set them equal to 0, what we'll end up getting is we'll get mz of x will be positive, and then we'll get p of x, the moment due to the force P is going to be equal to a positive P times x, so we can say that mz of x is going to be equal to negative P of x. Okay, so that would be true regardless of where you'd be along the x direction, because there's only one force being applied in this situation. Alright, so the other term that we need to know is the derivative of mz of x with respect to our applied load P. So if we take the derivative of mz of x with respect to our applied load P, it would just be equal to negative x. Okay, so those are our two unknowns. So the only thing we have to do now is we have to plug in those two unknowns into our integrals. Alright, here, and we'll solve for those. Solve for delta A. Okay, so just plugging in, you get delta A is going to integrate from 0 to L over 2, 1 over e to the I1 times mz of x. Sorry, so mz of x, I should plug in here, is going to be equal to minus P of x times negative x dx plus the integral of L over 2 to L of 1 over e to the I'm going to plug in for I2 is going to be equal to 2I1, all right, which was given to us here. Okay, and then it'll be multiplied. We'll have our mz of x term minus px, and we'll get our derivative with respect to p, which would be negative x dx. Okay, so we can just evaluate these two integrals. So the first integral, we'll just get 1 e to the I1. This will be the integral from 0 to L over 2 of p x squared dx, and then our second integral is to be equal to 1 over 2 e to the I1 times integral of from L over 2 to L of p of x squared again dx. Okay, so if we integrate p of x squared, what we'll end up getting for the first integral is we get p e to the I1 x cubed over 3 from L over 2 to 0. And then our second integral is going to be equal to p over 2 e to the I1 times x cubed over 3, but the bounds of this integral are going to be from L to L over 2. So if we evaluate these terms, we'll get p e to the I1 times L over 2 cubed over 3 minus 0. And then the second integral will be p over 2e I1 times L cubed over 3 minus L over 2 cubed over 3. Alright, so what we'll end up getting here is we'll get p e to the I1 times the length cubed over 24. And then the next integral is going to be equal to p 2 e to the I1 times the length cubed over 3 minus the length cubed over 24. Right? So if we combine all of these terms, what we'll end up getting is they all have p e to the I1 in them. We'll have the length, and they all have the length cubed term in them. So what we'll end up getting is we'll get 1 over 24 plus, if we convert this to, if we multiply the 2 through here, we would get this would be 1/6 here, and then the other term would be equal to minus 1 over 48. Alright, 48 is our common denominator, so we can put everything over 48. Alright, and then all our other terms here is just going to be equal to 2 plus 8 minus 1, or that's just going to be equal to a positive 9. So we'll get 9 PL cubed over 48. Sorry, I left out the Young's modulus term here, EI1. Okay, and that's our displacement at the end of our beam, delta A. Alright, so just to recap, what we did, alright, is we needed to define we needed to evaluate this integral on the right hand side here. Alright, so in order to evaluate that integral, we had to first split it into two separate integrals, integral 1 and integral 2, because of the change in the cross-sectional area, I1 and I2. And then we had to then define our function mz of x, which in this case was the same for both integrals, and we also had to define the derivative of that moment as a function of x with respect to the applied load at the point of interest, which in this case was p. All right. After that, once we plugged everything in, it was just evaluating an integral to get our answer.